So today we're going to talk about muscle structure and muscle function. And the skeletal muscles, like the bones, are designed to contribute to the body's need for mobility and stability. So muscle forces that are applied to the body have both a rotary and a translatory component. When I look at the muscle force vector applied by the patellar tendon, there is a component that is perpendicular to that axis. That's the rotary component. That's the component that adds motion. It produces the force that allows the rotary component to, the bony lever to move around its axis. At the same time, there's a stabilizing vector component. And normally that component will apply a load that approximates the joint, provides stability to the joint. So as the joint moves in and out of its open pack position, it provides more support during the open pack, and as we move into closed pack, we have less support. Now, muscles also have characteristics of extensibility, elasticity, and contractility. Those things allow the muscles to be stretched and to return to their resting length. Now, muscles have the ability to shorten and produce tension at their ends. That's what creates that rotary component. Fibers can shorten to typically half of their resting length, and they can be stretched to about 1.5 times their resting length. So the range between the minimal length and the maximal length of a muscle fiber is known as the amplitude of action. Now, the elongation that occurs varies proportionally with the length of the fiber and inversely with its cross-sectional area. So a muscle that has a larger cross-sectional area will not shorten as much as a long, strappy type muscle. Now, muscles are made up of two types of materials: contractile muscle tissue and non-contractile connective tissue. They're grouped so that they may individually or collectively contribute to the movement, but they rarely act individually. Most muscles work with other muscles, and they maintain a multitude of roles. So, how are muscles organized? Well, each muscle is typically thicker at its belly, tapers down and connected to the bone via a tendon or an aponeurosis. Covering the outside of the muscle is a fibrous non-contractile connective tissue called the epimysium. The epimysium is important in the smooth transfer of muscle forces to the bone. Smooth transfer of muscle forces to the bone. Muscle fibers are grouped into fasciculi, each containing approximately 200 muscle fibers. They're 1 to 3 inches long and contain the cell nucleus, the mitochondria, the myoglobin, the glycogen. And then each fiber strand contains hundreds of myofibril strands embedded in the sarcoplasm. And they're held together by the sarcolemma, and they're able to propagate nerve impulses. And then each fiber is then enclosed in the endomysium. The contractile unit is really the component of the fiber that is between the Z-bands. Here and here. And I'm not going to spend a lot of time on the sliding filament theory. You guys got that in anatomy and physiology. But I want to elaborate on a couple things that are important. And the things that are important from a kinesiological, it's all important, but the things that are important that I want you to keep in mind is this relationship between the cross bridges and the actin-myosin units. In a normal resting position, the actin and the myosin line up and have the ability to connect and contract in the presence of calcium. when the calcium creates the inhibitory effect on the troponin and the tropomyosin component. Just kind of keep that in mind, because if the muscle was lengthened, we may have fewer opportunities. The cross bridges may end up out here, where there's no actin for them to connect with, or in a very shortened position, they may be overlapping. They may be overlapping this direction. So the important component of the contractile unit is looking at the relationship in length for the actin and the myosin during the sliding filament theory. So you can review the sliding filament theory from your notes in your earlier classes. Now the functional unit takes into account the innervation of the motor unit, the motor neuron, and its innervation into the individual muscle fibers. The number of motor units that are innervated by a single motor neuron will vary depending on the size of the muscle and the function of the muscle. For example, there may only be 2 or 3 or 4 muscle fibers that are innervated by a motor neuron in the case of a muscle that requires fine motor control. So when you're looking at motion and function in your hand, an artist, for example, painting a beautiful painting will have much fewer motor fibers attached to any given motor unit. Whereas in the gastroc, for instance, there may be 2,000 muscle fibers attached to one motor unit. So much fewer motor neurons going to a much greater number of fibers in muscles that don't need that coordination, but they need to be able to generate a large amount of force in a short period of time. Now we can also look at muscles in terms of their fiber types. We have slow oxidative muscles. Slow oxidative muscles are those muscles that are really efficient at utilizing oxygen and allowing us to go for long periods of time. They're high concentrations of mitochondria. Tend to be smaller in diameter. Whereas the fast oxidative glycolytic we start to see a greater proliferation of glycolytic components. That's kind of where we are. Most of us kind of have in this nice blend of fast oxidative glycolytic. Power type athletes will tend to have more fast glycolytic. So when I look at sprinters and powerlifters and shot putters, they tend to have a higher concentration of fast glycolytic fibers. And lastly, we can look at muscle types by their size and shape. A fusiform muscle tends to be long, have a greater amplitude of action. Sartorius is a good example of a fusiform. A unipennate, the fibers are attached to a central tendon at an angle. Muscle fibers tend to be shorter, so their amplitude of action tends to be less. Semimembranosus is a good example. Some of the long toe flexors, good examples. A bipennate has a central tendon with this orientation of the fiber attachment at about a 45 degree coming off the central tendon on each side. Rectus femoris is a great example. A multipennate, good example is the deltoid. Fibers oriented in a number of different directions. And then lastly, A triangular muscle, pectoralis major, is a good example of that type of muscle. So what I want to do is continue on with the next lecture here, but keeping in mind the characteristics of extensibility, elasticity, the orientation of the actin and the myosin as we look at how the muscles develop the ability to generate loads and forces and contract and different types of contractions.